In this lesson, we're going to look at differentiating trigonometric functions. Differentiating the base functions, we have the following definitions. Y equals sin x leads to dy by dx equals cos x. Y equals cos x leads to dy by dx equals minus sin x. The reason we refer to these as the base functions is all the remaining trigonometric functions such as tan, sec, cosec and cot can all be defined in terms of sine, and we will come back to this a little bit later. Now in your notes you'll find that you've got some proofs. They're not definitive proofs, but because you can prove the derivatives of trigonometric functions using differentiation by first principles, and then use identities, and we'll talk about that in a moment. However, in your notes you'll find a copy of Taylor's series, and you'll see how sine and cos are defined in terms of Taylor's series, and they can show you the relationship between the derivatives, and it makes a nice alternative at this point. Now, there are obviously further derivatives because you've got tan, sec, cosec and cot, and so I'm going to state their derivatives and I'm going to give them to you without proof, but all of these results can be found by using the base functions sine and cos. I've omitted these proofs because it's an exercise that you should try and do independently, as they do come up in homeworks and they come up in the exam. So it's an exercise that you need to be able to manipulate and try and do for yourself. So the further derivatives are, if y equals tan x, dy by dx equals sec squared x. If y equals sec x, dy by dx equals sec x tan x. If y equals cosec x, dy by dx equals minus cosec x cot x. And if y equals cot x, dy by dx equals minus cosec squared x. So let's have a look at an example. We want to find dy by dx for these two examples. So starting with the first example, first thing to say about differentiating trigonometric functions is we have this cosec 2x. Let's note that this isn't a product. 2x is a function of x within the function cosec. So this is in fact a composite function, and pretty much all trigonometric functions are composite functions, apart from the ones that I've defined in the notes and in the last couple of slides, where you just have the tan function acting on x on its own. Every other time it's going to be on a function of x, whether that's 2x, whether that's 5 minus 6x, whether that's 3x squared. And so what this means is we need to use the chain rule pretty much every time that you're going to differentiate trigonometric functions. Okay. Now the way this works is, this isn't a quotient because it's not divided. There's no other function of x in this, so we know it's just a chain rule on its own. So we're going to start off, if I differentiate cosec x, I'll note it down here just for argument's sake, y equals cosec x. What I know is dy by dx equals minus cosec x cot x. Okay, so applying that here, I'd have differentiate the outside function. So differentiate the cosec x, I'm going to get minus. There's a coefficient of 3, so I'm just going to write it as minus 3 to start off with. And I get cosec 2x, because I'm going to leave that inside function alone, times cot 2x. And that's the first step of the chain rule done. I then need to multiply by the derivative of this inside function, so I'm going to multiply by 2. And so dy by dx becomes minus 6 cosec 2x cot 2x. And that's all there is to it. And every trig function you're going to find you're using a chain rule, because you're going to differentiate that trig function and then you're going to multiply by the derivative of that inside function. And if you just get into that habit, even when there's not a function of x and it's just, say, cosec x, you'll be in the habit of saying, okay, differentiate by cosec x, multiply by this derivative of x here, which means at the end you'd say times 1, and you'd probably not even bother writing the times 1. So if you remember that you use the chain rule every time you differentiate the trigonometric function, then you won't forget to use it in the important ones. Okay, so let's have a look at the second example. In this example, notice again, we've got a trigonometric function, but we've got a quotient this time. And so I've got a function of x on the numerator and a function of x in the denominator. So if I state u equals 5x squared, and v equals sine of 3x plus 1. I'm going to differentiate these and use the quotient rule. So in this case I'm using the quotient rule. Remember that I may have to use the chain rule alongside the quotient rule, just as we have noted in the previous questions using the chain product and quotient rule. So differentiating 5x squared du by dx is just 10x. No need for the chain rule here. Differentiating v, notice again I've got this composite function, so I know every time that I'm going to differentiate a trig function I'm going to use the chain rule. Differentiating sine, I get cos, so I get cos 3x plus 1, and then times the derivative of the inside, so derivative of 3x plus 1 is 3. So tidying this up, I get 3 cos 3x plus 1. Okay, so let's substitute this in now into the quotient rule. Remember, we have to start off, it's v du. Okay, so remember the visual display unit must get this order correct, so we're going to do v du, multiply this in our head, get it organised how we're going to do it. So we're going to start with that constant, and then any algebraic term, and then write the trigonometric function last. Okay, do the same for the other term, so I'm going to put a minus because I'm subtracting u dv. Okay, so u dv is these two terms here. Just think about expanding them and what that will come out as, and write it in one step. So I'm going to do the 3 times of 5, which gives me 15. Algebraic term doesn't multiply anything, so we're just going to put the x squared there, and this time I've got this is multiplied by cos 3x plus 1. And then on the numerator, sorry, the denominator, we're going to square the v term, which was sine 3x plus 1. So at this point, we've done most of the marks. We get most of the marks at this point. Remember that there's some additional marks potentially for factorising and simplification. So let's factorise. Common factors of 10 and 15 are 5. Common factors of x and x squared is x. Common factors of sine and cos, there isn't one. And please note that this bracket here, the 3x plus 1, it's not a factor. This isn't a product. Remember what I said in the last question. This is a composite function. 3x plus 1 is within the function sine, and it's within the function cos. So it cannot be taken out as a factor. So inside the bracket I get left 10 divided by 5 is 2, x divided by x is 1, and so I just get left with 2 sine 3x plus 1. Minus 15 divided by 5 is 3, x divided by x is x, and then, sorry, x squared divided by x is x, and then we get left with a cos 3x plus 1. So I haven't taken that 3x plus 1 outside as a common factor. It's not because I've forgotten to, it's because it's not a factor, it's part of a composite function. Last thing to do, just tidy up the trigonometric function underneath using the conventional way to write powers of trigonometric functions, putting that power on the trig function itself. And that is the question completed. So note that the quotient rule and the product rule, they are applied exactly the same way if you have trigonometric functions contained within them. The important thing to remember when working with trig functions is that you're always going to use the chain rule. Okay, so let's move on to something slightly more challenging. You may, in mathematics, you'll often be presented with not just a function embedded within a function, so a composite function, but sometimes you get functions embedded in functions, and further. So you get composite functions of composite functions. Okay. Now you may have come across these in exercises already. When you've done so, or if you do so in the future, you need to use the chain rule in a recursive fashion. And what we mean by that is that the chain rule has to be applied repeatedly, and then what we do is we apply it to the outermost function, and then working from the outermost function right into the innermost function, differentiating the outside each time, leaving the inside alone. Now, this doesn't make much sense without having a look at an example, so let's look at an example. We're asked here to find dy by dx when y equals 4 cos cubed 2x. Okay, so if I rewrite this, it's a little bit easier to see what we're saying here. Okay, I have 4 cos of 2x cubed. Okay, so this is, let's do outermost function. Okay, I then have inside here, this is another function inside, so this is the middle function, let's just refer it to that. for the time being. And to be honest, I would be very surprised if you go any further than this. And then we have this other function, which is the innermost. Now if you consider this, I've got the function 2x embedded in the function cos, which is embedded in the function cubed. Okay, and what we're going to do is we're going to work from the outermost function. So we're going to differentiate the outermost function first of all, leaving the inside alone. We're then going to differentiate the next function inside, so that's the middle one, the cos function, leaving the inside alone. And then we're going to do finally the innermost function. And each of these derivatives is going to form a product, so I'm just going to multiply them together. Okay, so I'm going to do each part in a different colour so you can understand what I'm doing. So dy by dx, differentiating the outermost function, so 3 times 4 is 12. I'm going to leave the inside function, or functions, completely untouched. Drop that power by 1, I get squared. Now I'm going to multiply by the derivative of the inside function. So I'm going to multiply. Now I'm going to multiply by dividing cos of 2. By the derivative of cos 2x. So first of all, I differentiate cos, because that's an outside function in that bit there. So I get times minus sine, and I have to use that 2x alone. And so I'll come from the outer to the inner. And finally, as part of differentiating the inner one, I've also got to multiply by the derivative of this. So I'm then going to times by the derivative of 2x, which is 2. And so as I said, I've applied this chain rule recursively. I've kept on differentiating the outer function and making a product working from the outside in. Okay, so that 12, so notice outermost multiplied 3 by the 4 to get the 12, left the inside bit alone, and then decrease the power by 1. Then focused on differentiating the cos. Differentiating cos gives me minus sine, I've left the inside function alone. And then finally finished off with that innermost function times by that derivative, which is times 2. Now if we tidy this all up, dy by dx is equal to, I get 12 times minus 1 times 2, so I get minus 24. I get cos squared 2x, so it's nice to write it back in the conventional, using the conventional power on this trigonometric function, times by the sine 2x. Okay, and it looks a little bit tricky at first, but with a little bit of practice, you'll notice it's just a slightly more complicated version of the chain rule. Okay, I hope that all made sense and that you was able to follow the examples.